Okay. Good evening, everybody. Yeah, I have received the homework from 3 people. I will discuss the homeworks tomorrow because today I wanted to discuss about principal component analysis, a very important part in your machine learning. Okay. Hello? Yeah, sorry, some people came. Okay, I think you guys can see my screen. Can you all see my screen? Is my voice audible to all? Are you all able to see? Yes or no?
Yes, sir.
Yes, sir.
Okay, okay. So let us start with the component analysis. So what is principal component, anybody? We have done some Principal component analysis is a dimensionally reduction method that is often used to reduce the dimensionality of the large data set by transforming the large set of variables into smaller ones that contains most of the information in the large set. Along with that, in principal component analysis, whichever the component is more prominent, we can distinguish it. Suppose like if we have two types of data sets, as we had seen in the last classes, suppose data set 1 and data set 2, but if you want to as like if we have a height of father and height of son, if we apply this principal component analysis, both the heights will get separated and you will be able to see the both the components separately. And above all, if you are giving specific colors to the values or to the data sets, that will also be visibly seen in your graphs or whichever component you are using for the visualization. Okay, so why the factor or component analysis? We study phenomena that cannot be directly observed, because the thing is that if you are giving two particular data sets, how to take it or how to go ahead with that. Example like personality, intelligence, and then you have underlying factors that govern the observed data. Further, we want to identify and observe the underlying latent factors rather than the observed data. Because we are getting some observed data, but we want to get some hidden factors in that. Example, the topics in the new articles or transcriptor fractions in the genomics and so on. So we will be identifying the hidden factors there. We want to discover and exploit the hidden relationship. Example like beautiful car or gorgeous automobiles are closely related. So are drivers and automobile. But does your search engine know this? We don't know. The search engine may not know. So we can actually use a component analysis for that. This particular component analysis, it also reduces the noise and error in the results. We have too many observations and dimensions. Usually in the component analysis, usually the graphs will be mainly 2D or 3D. Even 3D graphs are also supported. I think you have seen in the last classes. We have too many observations and dimensions to reason about or obtain insights from, to visualize too much noise in the data, need to reduce them into smaller set of factors. If you have a data set, you want to be reduced into the specific small factor from the data set. As from the whole genome, you can select directly the expressed data. If you have attended the class on this transcriptomics, you are getting the one graph called as principal component analysis. So how the components are coming, it is from the expressed genes. So from the whole genome, you are getting the expressed components. Better representation of data without losing much information can build more effective data analysis on the reduced dimension, space classification, clustering, and pattern recognition. Combination of observed variables may be more effective basis for the insights, even if the physical meaning is obscure. Okay, now what are the components or the factors? Discover a set of factors or dimensions or axes against which to represent or describe or evaluate the data. So based on the factors, we are evaluating the data set. So we are not exactly seeing the plots of the data set, but rather we are in the plot, we are seeing the specific factors in the plots. For more effective reasoning, insights, or better visualization, it reduces the noise in the data. Definitely, the repeated values will be there, will not be there. Typically, a smaller set of factors, dimension reduction happens, better representation of data without losing the much information, and can build more effective data analysis on the reduced dimensional space, classification, clustering, or pattern recognition. Factors are combination of observed variables may be more effective basis for insights even if physical meaning is obscure. Observed data are described in terms of these factors rather than in the terms of original variables or dimensions. Okay, so what exactly it is? Areas of variance in data are where items can be best discriminated and are kept underlining phenomena that are observed. That is areas of greatest signal in the data. This is the whole motto for your principal component analysis. Areas of greatest signal. We can do so many analysis in our data set. Suppose we are getting 5 or 6 data sets. In that, which is the best? So you can observe, you can do analysis using the PCA. PCA is one of the major component you can by which you can do this one any this data analysis projects. If two items or dimensions are highly correlated or dependent, they are likely to represent highly represented phenomena. If they tell us about the same underlying variance in data, combining them to form single measure is reasonable. That is parsimony or reduction in error. So if you want to combine related variables and focus on uncorrelated or independent ones, especially along which the observations have high variance. So if it is like uncorrelated, that is non-correlated data, you can do with observation, you can do with high variance. We want a smaller set of variables. Rather, we are smaller set of variables. We will from the main data set, we will take the smaller set of variables that explains most of the variance in the original data in the compact and insightful manner. So from the component analysis, if either it is correlated or non-correlated data, we will check for the simpler data set from the data set which we are working on it. So we may not exactly use the output may not be exactly the actual data set, but it will be a part or subset of the original data. So what if the dependence or correlations are not so strong and direct? Look for the phenomena underlining the observed covariance or codependence in the set of variables. These phenomena are called factors or principal components or independent component depending on the method used. Okay, either you can keep the term as factors or principal component or independent components. Factor analysis based on the variance, covariance, correlation, independent component analysis based on the independence. So you can check it out both in factor analysis and independent component analysis. In the independent, it is based on independence, but if it is a correlated data, correlated means one data set is dependent on the other data set, you have to do factor based analysis or based on the variance. Okay, so most common form of factor analysis, that is the principal component analysis. The new variables or dimensions are linear combinations of the original ones. As you can see, throughout I am telling that in the data sets are the linear combination of the original ones. The original one will not be there, but actually will be deriving some factors from the original ones, are uncorrelated with each other, maybe correlated, maybe uncorrelated, both ways. Orthogonal in the original dimension space, capture as much of the original variance in the data as possible, and that's why they are called as the principal component, because they capture as much as the original variance in the data as possible. So this particular, when I will be giving you this PPT, you can see this particular HTML page to know more about this PCA. Okay, so in the PCA, you will be, as you will see, you can get the data in two types of access. Like PCA1, it will be in one side. PCA2, it will be other side. Means you will, the data will be separated. Orthogonal directions in the of the greatest variance in the data. I think when I had used the transcriptomics, you might have observed that in the PCA the expressed genes were got separated in different axes. Axis in the sense like in the separate part of the graph, you might have seen it. So which was better and which was more what you call expressed, it was based on the PCA value. So orthogonal directions of the greatest variance in the data, projections along the PC1 discriminate the data most along any one axis. So PCA1 already it is told that this particular, here it is PCA1. So PCA1s here are more prominent data set, or these are the more prominent factor. That's why it is called as PCA1. So whenever you are doing this, you will be directly getting which are the PCA1 and 2. Okay, principal components. First principal component is the direction of the greatest variability covariance in the data. This is a very important point to note. So very important point, first principal component is the direction of the greatest variability or covariance in the data. Second is the next orthogonal or the uncorrelated direction of the greatest variability. So first remove all the variability along the first component and then find the next direction of the greatest variability. Principle underlined in PCA. Linear projection method to reduce the number of parameters. Transfer a set of correlated variables into a new set of uncorrelated variables. Map the data into a space of lower dimensionality and form unsupervised learning. When I was taking the machine learning, I think you have observed this supervised and unsupervised learning. So PCA, it was coming under this unsupervised learning, if you remember. Properties, it can be viewed as a rotation of the space as defined by the original variables. So original variables will be there, but once you are plotting the graph, you will be seeing the two components distinctly. New axes are orthogonal and represent the direction with maximum variability. So computing the axis, data points are the vectors in the multi-dimensional space. Projection of the vector x on axis, that is u dot x. Anyway, the plot you will be getting it when you will be doing the particular calculations. Direction of the greatest variability is that which average square of the projection is the greatest. So that is mu is E mu square over the x is maximum. Anyway, no need to worry about these calculations because you will be getting the value of your PCA1 and PCA2 and so on. So once you are getting the value, no need to worry, but it is good to know the formula, how it is happening. because anyway with the R or any other software which is designed for the PC, they will do it automatically. But still, it is always good. The underlying statistics there, it is always good to know, because whatever I'm teaching from the beginning, it is all statistics. So good to know what comes inside. So we subtract the mean along each direction, each dimension, and center the original axis system at the centroid of all data points for simplicity. This direction of the u, not it is the mu, it will be is the direction of the first principal component. So usually this is the first principal component because it is in this direction, or others are all orthogonal to each other. Similarly for the next axis and so on. So the new axis for the eigenvectors of the matrix of correlation of the original variables, which captures the similarities of the original variables based on how data samples project to them. Okay, next is the PC's principal component variance and the least squares. First, PC retains the greatest amount of variation in the sample. The k, that is one particular value, that is the k-mer you might have used in the calculations. K-mer, that is kth PC retains the kth greatest fraction of the variation in the sample. The kth largest eigenvalue of the correlation matrix C is the variance of the sample along the kth PC. The least square view PCs are a series of linear least square fits into a sample, each orthogonal to all previous ones. How many? It is unspecified. It depends on us how many data sets we provide. For n original dimension, correlation matrix is nxn, n into n, and it has up to n eigenvectors. So n pieces means it depends on how many data sets we give. Where the dimensional reduction come from? So can ignore the components of the lesser significance. So you can see that PCA1 will be the highest. You will be getting the values when you are doing this PCA. So PCA1 will be the highest and so on, and slowly towards the end the values will be reducing. So in the graph you may not see all the PCA, maybe till 1, 2, 3, 4, 5 maximum. After that you may or may not see. So the R or the R plot may ignore the less PCA values. You do lose some information, but if the eigenvalues are small, you don't lose much. N dimensions in the original data. Calculate n eigenvectors and eigenvalues. Choose only the p eigenvectors based on the eigenvalues. Final data set has only p dimension. So like this, it will be seeing in your PC analysis. So PCA versus a factor analysis extracts all the factors underlying a set of variables, the number of factors, the number of variables, completely explains the variance in each variable. In a factor analysis, also known as principal axis analysis, analyzes only the shared variance with no error. Okay. Vector space model for documents. It's not needed for you. Why I kept it? Okay, some of the problems looks for the literal terms matches. Terms in queries, especially the short ones, don't always capture the information need well. And polysemy. And what if we match against the concept that represent related words rather than the words themselves? So you can see that in the for the PCA, suppose if all the information is not given, so it will be like the computer will be difficult for it will be difficult for the softwares to give you the exact values. So relevant doc may not have the query terms. Sometimes the query terms may be missing. Irrelevant docs may have the related query terms. Okay, then the LSI, latent schematic indexing, uses statistically derived conceptual indices instead of individual words for the retrieval. It assumes that there is some underlying or latent structure in word usage that is obscured by variability in the word choice. Key idea here is instead of representing the documents and queries as vectors in a T-dim space of terms, they represent them and terms themselves as vectors in a lower dimensional space whose axes are concepts that effectively group together the similar words. These axes are called as the PCA components of the PCA. So some examples. Suppose we have the keywords like car, automobile, driver, or elephant. We want queries on a car to also get docs about the drivers and the automobiles, but not elephants because they are related. What if we could discover the cars, automobiles, and drivers axes are strongly correlated? Yes, they may be correlated, but the elephants, yes, it will not be correlated. How? Via correlations observed through the documents. If the docs A and B don't share any word with each other, but both share a lot of words with doc C, then A and B will be considered similar. Example, A has cars and drivers, B has automobiles and drivers. So in this manner, you can correlate. When you scrunch down dimensions, small differences or noise gets glossed over and you will get desired behavior. So you can see here how you can you will be getting the data set and how you can analyze it. This is not needed. So even PCs you can see using this also, which are the principal components. Okay, these are actually the express genes here. Okay. These are all the various data sets and how they are correlated. So you have here medicine data, and you can see how they are put in the graph and correlated. You can see here how both the components are separated in the graphs. And here also. Okay. SVD, last time we had seen about this SDV. There is an implicit assumption that the observed data distribution is a multivariate Gaussian. Can consider as a probabilistic general model. Latent variables are Gaussian suboptimal in the likelihood terms for non-Gaussian distribution. Employed in signal processing for noise filtering. Dominant subset contains majority of information bearing part of the signal. Okay. SVD defined basis provide the PR improvement, that is the principal component, and regulations improvement over the term matching, interpretation difficult, optimal dimension, that is open questions, variable performance on the large collections, and supercomputing muscles are required. In probabilistic approach, they provide improvements over the SVD, clear interpretation of the decomposition, optimal dimension, open question, high variability of results due to non-linear optimization over huge parameters space, improvements in the marginal in relation to the cost. Okay, limitations are the maximum variance dimension, relevant dimensions for the preservation, that is the relevant component analysis and Fisher discrimination analysis. Should the goal be finding independent rather than the pairwise uncorrelated? Limitations of a PCA, the reduction of dimensions for the complex distribution may need non-linear processing and curvilinear component analysis. A non-linear extension of the PCA preserves the proximity between the points in the input space, that is local topology of the distribution. It enables to unfold some varieties in the input data and keep the local topology. That is all. Okay, now everybody can some of the examples I will show you. Okay. The principal engine face looks like a bland androgynous average human face. Applications. You can see how the data are separated in 34 patient dimension of 8,973 genes reduced to 2. So you can see how the clustering is happening here. PC of the genes in the leukemia. This one is one type in the heat map also you have seen, that is in the phylogeny, how the particular gene components are clustered together. Okay, this is again heat map and how the phylogeny is happening here. Okay. Okay, all please open your R Studio. We will perform this. Okay, please set your working directory. Okay, just check it out if this library is working. Okay, it's working. So you are doing a correlation study between the father and father and son height. Okay, everybody is doing this? Yes or no?
Yes, sir.
Okay. Okay, so data is loaded. Okay, this is the correlation. Here you are making it. Here we are trying to predict the son's height based on the father's height. So son's height is taken as y here and father's is x. And this is the machine learning technique, the regression technique. Okay, just do this. So in this case, we are actually doing the approximation distribution of the y, which we are taking as normal. And here we are told that the father is has randomly selected his son's height as 71 inches, which is given there. So we are selecting the 70, that is 1.25 SD taller than the average. So you can see here in the area of 71, that is we are taking, that is the average, and here also we are getting the same. Okay. So when you are giving my par 1,2, it is actually in the same place, it is putting two figures together. Here we have kept the sun's height, we have taken it, that is, and we have given that father's height as 71 directly. Here the regression line provides an optimal prediction function for the y. Okay, take the next code. So we have done the regression. Now we can do analysis with the tissue gene expression. Check it out if these two codes are working. Library, tissue gene expression. Check it out if it is working for you or not. If it is steps. Just check it out if it is working or not. Is it working for everybody? Yes or no? You all are silent. Chinmay?
No, sir. No, sir. It's not
Working, sir.
Not working. Saidevya, why? Which code is not working?
Library tissue gene.
Then you have to. You did not attend the last class. I had given the code right.
Sometimes CSV files doesn't open properly.
Okay. Others?
It's working, sir.
Shruti,
It's working.
Shruti, Rajapriya, Saidev, Rajapriya, Priyanka.
Got it, sir.
Got it. Only for Saidevya it is not working. So Saidevya, take that last day's codes. Condition is that check your working directory.
Okay, sir. I will check it.
Yeah. So I have given the two lines After that, you can put the library and it will work.
Okay.
Okay, so give the table and see the tissue table. So you are removing the placenta here actually. That is a not operator. So you are doing the mean and you are removing the PED. So print the mean. So you can see that there is one function called KNN, that is K neural network. We had seen that in the last class, KNN. Okay, so then your command is library. If this library doesn't work, you have to install the package. We are getting the labels. Give the head command to see the genes. So we can see that the tissues are fairly equally represented across the folds. So you have 10 folds here, tissues are equally represented. To reduce the dimension of the data, the particular command is given CMD scale. All are getting the results? All got this particular plot, the PCA plot here. You can see how the components are separated. So you are checking the error rates, how much error it has come. So everybody got this PCA diagram? Yes or no?
Yes, sir.
Okay. So finally plot the error plot. So, so final codes are to see the gene expression. Again, we have used the CMD scale function to the entire data set to create smaller ones for illustration purpose. So from the in the PCA, if you want to create the smaller data sets, can use this CMD scale function. Okay, so we have got the misclassification error plot. Got everybody? Everybody got this? Yes or no?
Yes, sir, I got it.
Okay, others?
Doing so.
Okay. Okay, everybody got it? Yes or no?
Yes, sir, got it, sir.
Everybody? I think Chinmay got Gayatri,
Got it, sir.
Geeta, Haripriya,
Got it, sir.
Milan Prabhu.
Got it, sir.
Okay. Priyanka Rajapriya. Rishikesh.
Got it, sir.
Okay. Sai Divya and Shravani.
Got it, sir.
Yes,
Okay.
sir, got it.
So everybody has got it, fine. Okay, so I will be ending it here. So tomorrow again we will be continuing with the. Actually, tomorrow what I will do, I will take that data set which I had given, and we will perform the analysis. We will take one sample data set and we will do the PCA analysis again with this different data set. Already we are done with one internet-based data. Anyway, all are internet-based data only, but we'll take some separate data set and we'll work tomorrow for the PCA. So, so it's the clinical analysis and this one Bayes theorem. Let me see if tomorrow I can do it. The Bayes theorem, and if that is fine, so from the next week, let me start with the project. I will give you some project topics with a few code. Let us see how you guys are doing it. Okay, then. Thank you. See you all. Good night.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah, thank you. Good night.
Good night.
Good night, sir.